So yeah, so we can start. Yeah. So hello everybody. This is Luboš Prikl from CFD Support and Radek Maca from CFD Support. Welcome to the webinar on Turbomachinery CFD, which is a CFD simulation workflow for all standard rotating machinery. Just in case of any technical problems, feel to contact us in the future and we will gladly answer all your questions or reminders. The test case for today is axial pump. Please let me introduce ourselves a little bit. So this is me. My name is Luboš Prikl. I'm co-founder and managing director of CFD Support. Today I'm sitting here with my colleague and friend, Radek Maca. Hello, Radek. Hi. So how are you today?
Thanks, Luboš, for asking. I have a great day today, and yeah, it's a pleasure for me to be here with all the participants of today's webinar.
Okay, thanks. So it seems we are ready for the webinar. Yeah, I will also say a little bit about Radek. So Radek is head engineer and senior developer of CFD Support, and he's extremely smart guy and extremely friendly and great person. So it's a pleasure to have him here today. Okay, I guess I'll switch my camera off for now, and I'll start the webinar. The webinar is going to take up to 1 hour, depending on the number of your questions and reminders. There will be 3 parts of the webinar. In the first part, I will give a general introduction to Turbomachinery CFD. I'm gonna point out the main features and its benefits. In the second part, Radek is going to show how to simulate a pump in Turbomachinery CFD. He's going to take care about the technical part of our webinar and presentation. And finally, in the last part, there will be a Q&A session dedicated to your questions and my answers. So feel free to put your questions to the special window below, or you can also send your questions or reminders to our email to info@cfdsupport.com, and we will answer your questions later in this webinar. Especially in the beginning of the webinar, we are going to be quite general, but feel free to ask about the details and we will gladly provide all the details. Okay. About the CFD Support, the CFD Support is a private engineering company dealing with computational fluid dynamics. We are used to deliver complete CFD engineering projects, as well as open form support and development, open form training, and of course our flagship product is Turbomachinery CFD. Turbomachinery CFD, so the webinar is about Turbomachinery CFD, so let me start with a brief description of what Turbomachinery CFD is. So Turbomachinery CFD is a unique software based on OpenFOAM. It was designed for CFD simulations for all rotating machinery such as pumps, fans, compressors, turbines, water turbines, both radial and axial machines, both compressible and incompressible fluid flows. Turbomachinery CFD is complete CFD workflow that covers all the engineering steps from the pre-processing over the simulation run to the very detailed post-processing of the results. It's independent on any other software, so it's comprehensive. It's complete. Let me put just a quick review of its unique value proposal. Number 1, is Turbomachinery CFD has no licensing policy, which means our clients can keep Turbomachinery CFD forever, and they can use it for unlimited number of users, jobs, or cores. So it's in all the ways it's unlimited. And of course, that gives the investment in Turbomachinery CFD a permanent value. Number two is Turbomachinery CFD is fully automated, which means the workflow is automated from the initial data to the final results report. It can be run by a single command or a single click, and all the process is being done automatically. And for this reason, Turbomachinery CFD is extremely effective. Number three is we deliver extraordinary technical support, and we are proud of it because we keep custom approach to every customer, to every issue, and we are very flexible. We never leave behind any issue of any of our clients. We support our clients in matters, also in matters out of Turbomachinery, like numerical mathematics, physics, CFD, IT, or even software engineering. Yeah, and the fourth is the real tutorials are included, so the user has no doubts about the best practice settings. There are real machines included that are already preset, so you can basically take one of those tutorials, replace the geometry with your own. You just modify the settings where it differs and run the simulation. So those are the key benefits. There are also many other benefits of using Turbomachinery CFD. I'm not going to go for all of them. These were the major ones. Turbomachinery CFD is available both for Linux and Windows operation system. And by the way, in today's webinar, we work from the Windows operation system, but the Linux workflow is very the same or exactly the same. So it's always your choice which operation system to choose. The Turbomachinery CFD workflow is fully served from a graphical interface, a GUI. The graphical interface of the Turbomachinery CFD is ParaView. You can also work from a terminal, but most of the people prefer to work from the graphical interface. Of course, Turbomachinery CFD can be run on clusters or clouds to scale your CFD simulations in a big way. The decision is always up to you. Turbomachinery CFD can be, or the workflow can be scripted in Python. Turbomachinery CFD is transparent. The trial version is available for free for 1 month period, so anybody can try it, and afterwards he or she can decide to go for it or not. The tutorials are available. Every single simulation has its detailed report in web responsive HTML format. The Turbomachinery CFD also includes CFD processor, which is a special software tool for automating of OpenFOAM cases. And perhaps the most important information from today's webinar is all the information is available online. So you can visit our website and you can read everything. You can download everything. You can really find what to do. I think it's time for our live example. So, which brings me to back to Radek. So, Radek, are you ready for the live demo?
Yes, I am. Yes, I am.
Okay, so I will disappear for a while, and I switch the presentation to you, and now it's up to you. So, yeah, good luck.
Okay, hello again. So please let me start first to show you how easy it is to manage and run the today's case, which again it will be the axial pump. So first I will start how to show you how easy it is to manage it, to run the case. Then afterwards, in more details, I will present where a TCFD case can be set up and how it can be set up. Afterwards, we can go through the report. I will show you what information our reports provides. And at the end, I'm going to show you some advanced post-processing visualization in ParaView. And it is. Okay, so we simply start, as Luboš already said, all information can be found at our web pages. So to start to work with today's case, just go to our web pages, cfdsupport.com, go to the download section, go to the download cases, and here at the first place there is the axial pump tutorial. So simply input your email address and download the case. Okay, I have already downloaded. So afterwards I can go to my favorite file browser. For example, I am using the Total Commander, but you can also use any file browser. So I will go to the working directory of OpenFOAM, which is at my C disk in OpenFOAM. I'm using the newest version, 16.10 version of OpenFOAM for Windows, and the newest version of Turbomachinery CFD. Then I go to my home directory, to the run case, and here I have today's webinar. And from my download folder, I will just copy the axial pump case. I go inside the folder, and as you can see, the starting case is really simple. It just includes the file with the mesh. Today's tutorial consists of an external mesh, so our software provides both external meshes and the mesh which is directly created within our software using SnappyHex mesh utility. So here is just the parts of the geometry which was converted from, I guess, MSH format. So here are just impeller, inflow pipe, outflow pipe, and stator part. And here is simple configuration file. So just click on it, and the ParaView appears. So first, just click on Apply. In this section, here are the setup of the case. I will go through it later on. After that, we can apply the plugin which is called TCFD Manager, which can manage all the procedure or the workflow for OpenFOAM. So click on Apply. Here I can set my computation directory. So it's up to you. For example, my dir, and click on Apply. Afterwards, the management of the computation is really simple. First, just click on Write Case, which creates the OpenFOAM case with all necessary files and parameters. So now the case is written. Afterwards, I have two options. I can click all meshing process, computation, and post-processing using one click, which is similar to click first on Create Mesh, then to run calculation, and then to update report, for example. So I will click on Run All. So first steps, in the first step, it creates just the mesh. In our case, it puts the external mesh, modify it for the OpenFOAM purposes, and save it to appropriate directory for OpenFOAM. So afterwards, the mesh is done. It simply run the simulation, and you can directly read any information from the status bars. and afterwards you can, anytime during the computation, you can click on update report and you will see the actual information about your computation. Or you can, for example, set the time interval to be to update the report automatically in this way, for example. So you can see here the status for the first point computation. It means for the computation for first for the first point with the given initial and boundary condition. You can see the estimated time of computation. You can compute more speed lines for a particular machine, and here's the overall information of the computation. You can anytime you can, for example, if you see that the computation is converged, or for example the efficiency is fine, you can skip to the next point and so on. You can abort the calculation, and again I can update the report, and you will see directly in this window the report. So about the details of the report we will talk in, let's say, 5 minutes. Okay, so for now I will abort the calculation. So that's all, and the computation is run, and at the end you will see all the information from your computation. So back to the second point of my part. So how the case is set up. So you have two options. First option is to set up so-called CFD configuration file. So if I open it, it contains, let's say, 50 parameters or 70 parameters which are set up for the computation. So you can directly change it here, open it, and run the simulation. Or the same modification can be done directly from the graphical user interface. So again, I will just open it, click on apply, and in this left window you can set all parameters of the computation parameters of the particular machine. So for this case, the machine type is pump. We provide many other machine, for example, compressors, fans, turbines, water turbines. Here you just define the coordinate system in the usual way using origin and the axis. You can scale the geometry. If your input geometry is in millimeters, you can scale it to meters and so on. Physical settings, you can set up the gravitational acceleration, dynamic viscosity, reference density, reference pressure for incompressible cases. For fans, for example, you can choose between compressible and incompressible cases by clicking on it. You can change, for example, for fans, you can change fluid to air. Turbulence settings, the current version provides K omega SST and K epsilon in default. So this computation will be run using K omega SST. For example, if you click on this advanced properties, you can, so for more skilled CFD engineers, it can be set up the parameters of the turbulence settings can be changed, of the turbulence model can be changed. Here you can compute more speed lines. For example, if you, for compressor, you can generate full compressor map using, for example, 3 or 4 speed lines. In this panel, you define the rotation speed. You can choose between radians per second or revolution per meters. In this case, the revolution direction follows the right-hand rule. So in this case, this value is negative. For each speed line, you can compute several points from just 1 point to the 10 points. For each point, you defined number of iteration to be run. For steady state cases, for unsteady state cases, just define the time for each iterations. Inlet boundary conditions. So here we have for the pump, we have the volumetric flow rate at the inlet. So first point has 14 cubic meter per second, second point 13, and so on. Here are initial settings for turbulent energy intensity and turbulent dissipation. At the outlet, you can set fixed pressure or outlet vent, boundary condition. Here are preset atmospheric boundary pressure at the outlet for this case. Simulation settings. These settings is run using steady state case because, as you can see here, here are the input geometry. So it consists of just of the segments. So here is the white is inlet pipe, the red one is the rotor part, here is the stator blades inside this green region, and outlet pipe is the blue region. You can choose between first and second order numerical schemes. Here you can set up the averaging window, so all quantities will be averaged within the window of size 100 iteration. There is a tool to check the convergence, so if the efficiency, if the residuals, if other parameters are converged properly, it stops the iteration. For example, if we set 5,000 iteration, so if the convergence check is reached, it can stop earlier, for example, within 2,000 iterations, so you can save the time using this convergence check. Well, there are, let's say, more advanced parameters, relaxation factors. Here, important parameter inertial conditions for the pressure, for the velocity, for the turbulent quantities. And within this window, you can set up manually the topology of your case. So directly you can see the changes in this graph, in this sketch. So as you see, we have 4 components which is connected. For example, component 1 with component 2 is connected using AMI approach, and because I guess that rotor part has 8 blades and the stator part has 9 blades. So on this interface between red and green part, the mixing plane approach must be applied. So it is set in this way. For each component, you simply pick up the type of the boundary. So for inlet, just the inlet. For the outlet, between the components, you will just pick up the outlet interface or inlet interface. For walls, you set walls. On the periodic parts, it means on the periodic parts of the segments, you should impose the rotation AMI boundary conditions, and so on and so on. For the interfaces between 2 components, you can choose how many mixing planes should be used. If you set 0, it means there will be AMI applied. Or, for example, for component 2 between the rotor part and stator part, in this setup there is 10 mixing planes. So 0 means AMI connection. More than 0, so 1, 2, 3, etc., means mixing planes approach. Okay, so what I didn't say, that one component is rotating, so you can check it here, rotating components, and so on and so on. If you use not external geometry, you should you should define the background mesh size for the snapping, but for this case it is not relevant parameters because we are using external meshes. So roughly speaking, it is basic setup, which usually all the parameters for a particular machine is set as the default values with respect to the best practice setup. So let's say for those who starts with using CFD and with using TCFD, there are just few parameters to be changed. And afterwards, again, you click on apply, then click on the TCFD manager and run the simulation. So when the simulation is run or during the simulation, you can see, so here's my computed case, you can see the report which includes all important parameters of the computation. So for example, first section, the simulation statistics, includes the name of the case, number of points to be computed or which was computed, machine type, rotation speed, number of components, so how many parts, from how many parts the mesh consists. For each component, you can see how many cells it has. Here, important parameter for turbulence modeling, Y plus value. You can click on details that for each wall boundary, you can see the minimum, maximum, and average Y plus value. Overall computation of time, this case was computed on my laptop, which performance is really pure and it takes 5 hours. Fluid name, water, compressibility, incompressible case. Then in second section, for a pump, you can see a head for a given point and the flow rate. In the section efficiency, you can see the efficiency for each point. Each section has two graphs. First, in the first graph, there is a final parameters at the end of the computation of each point. So final results, and you can also see the time evolution during the computation of each variable. So here you can see the efficiency during the time. Here the torque for each point and during the time. Total pressure differences between inlet and the outlet. Total pressure differences per each interface. So, for example, total pressure differences at the inlet between the stator and rotor part and at the outlet. Again, also we can see the values for each interface. Velocity magnitude per each interface, and circumferential and meridional angle. So we can follow this angle, how if the blades are defined properly or not. and that is all for this report. Well, all this information, if I go back to my file browser, and here's my computed case. So if you go to your directory which you defined, so here you can see complete computed case with all setup of OpenFOAM. You can see in the post-processing, you can read anytime values of efficiency during the computation. So if I open it, so for example, here you have values for each iteration, each parameter, for example, efficiency, average value of efficiency, mass flow, volumetric flow, etc. So anytime can be found in this for the advanced post-processing thing and for the advanced evaluation, but all the basic are directly stored in this HTML report, so you can anytime open it in your internet browser and see the results. Okay. So and in the last part, I would like to show you some post-processing tools. So basic post-processing can be done directly within the ParaView. Just clicking on this case file, case.foam. Click on apply and you will directly see the results. So if I go, for example, to the last time step, which is the last computed point, you can see pressure, for example, total pressure, and so on. And our company developed two special plugins for ParaView. First is meridional average, which computes the meridional average for the geometry, and turbo unwrap, which can be used for blade-to-blade view. So I have prepared it. So first, the meridional average. The usage is simple. You just open the case. On the case, you check just internal mesh. Then on it, you apply the meridional average. The setup is easy. Just define the axis, origin, and the resolution of the raster on which the average will be computed. So then click on apply, and afterwards you will see the meridional average of your geometry. So it's nice to see the pressure, there is a pressure drop at the rotor part, and so on and so on. And the second plugin I would like to show you is Turbo Unwrap. So again, you apply the Turbo Unwrap on your case. In this case, you have to check here the internal mesh, and you have to check the hub part and shroud part of the part of the geometry you would like to unwrap. So in this case, it is a rotor part. So if I go to the Turbo Unwrap, here you just check this for the unwrap mesh, internal mesh. As a hub, you check the impeller hub. As a shroud, you just check the impeller shroud. Axis origin is set as in the usual way, and the break means the direction in which the wheel will be cut. So if you have full wheel, it is easy to imagine. If you just has just one blade, just mean the proper place to unwrap the one blade, and afterwards you unwrap the one blade. You can use the Infilters transform tools to create many blades, and on it you can just, for example, make a slice to show just the let's say the slice at relative radial coordinates. At the radial coordinates. For example, afterwards you made this turbo unwrap, you will see the mesh which is transformed to the box of size 1 × 1 × 2p. So it really unwraps the wheel, and the z direction means the z direction equal to 0 means it is a hub, and z direction equals to 1 means the shroud. And afterwards you can apply a slice with the given coordinates 0.5, and it makes a slice in the rotor part which corresponds to the coordinates 0.5. It means in the middle between hub and shroud. And on this slice you can visualize, for example, pressure, or you can evaluate the streamlines using this surface-lets representation. So I guess that it is now the time to go back to Luboš. So Luboš, the virtual floor is yours again.
Okay, Radek, thank you very much for giving this example on axial pump. It was a pleasure to watch it. So I guess I should become the presenter, which brings the presentation back to me. So it seems it's back on me. So Radek, thank you for your part, and I will continue in our webinar. So there was a live example. Okay, there are some, just a little bit of Turbomachinery CFD, how to get it. Yeah, so we provide a demo version, a trial version of Turbomachinery CFD, which is available online. Anybody can try Turbomachinery CFD for 1 month. So anybody can try, and afterwards he or she can decide to go for it or not. The Turbomachinery CFD is paid software. It's paid and it's perpetual. So actually, what is paid for is the delivery and the technical support and updates and maintenance of the software. So we believe Turbomachinery CFD is extremely affordable. We decided to fight hard for the universities. So universities pay only 3,000 euro a year, and private companies pay 12,000 euro per year. Please contact us for more details. We will gladly answer all your questions on pricing and terms and conditions of using Turbomachinery CFD. Which brings me to our last part of our today's presentation and webinar, and it will be a Q&A session. So I think now it's time to go to your questions, and we will go through them and answer. So please feel free to put your questions. It's still time, so feel free to put any of them, and we will go one by one and answer them here. We still have like 20 minutes, so I believe we can make all of them. So I have here the first question. It's from Dr. Beagle, and does Turbomachinery CFD support transient CFD simulations, or it is just a steady state? So, Radek, may I ask you, would you answer this question, please?
Yes, sure, I can. Can you switch me the? Okay, I will make a presenter for me again. So I hope you see again my screen. So if I go, okay, I will open again the case. So let's say our axial pump segment is not a good example to run the transient case, because on this segment part is not available to run it. But for the full wheel part, for full wheel geometry, it is easy to manage it, because if you go to the settings part, and here in the simulation settings, you just pick up the steady state plus transient. It means that each PID line is computed starting, or each point is computed starting the steady state computation, and from the steady state computation it is run the transient case. And as you can see, for example, here you can define for each point the time in seconds, or in more simple way, you can define just how many revolution you would like to compute. For example, here the default value is 4 revolution. So yes, it is our software provides both steady state and transient cases for computation.
Okay. Okay, Radek, thank you for answering this one. There's another one. Karim is asking, is it possible to select different turbulence models? Yeah, is it possible to change the different models? Would you answer this question, Radek? Yeah, okay, I can answer it. So yes, of course, by default in Turbomachinery CFD, you can select K omega SST and K epsilon turbulence model, but of course, Turbomachinery CFD is compatible, fully 100% compatible with standard OpenFOAM. So you can, after writing your case down, you can change the turbulence model in case settings, and then you can run the simulation, and it will be run with your turbulence model you have selected, with your constants, with your settings, with whatever you like. So yes, you can change it. There's just a little bit manual work in it, and also you can put the script or really make it automated. It's pretty easily. But by default, in graphical interface, there is only K omega and K epsilon to be selected. Yeah. So some other questions. Yeah. So I will read the next one. We have many questions, so thank you for them. So let's go one by one. The next one is for the Sandeep Nair is asking, for Windows OpenFOAM, do we need zero, constant, and system? Yes, we need it. Yeah, because it's back to me. Okay, Okay, yeah. So yes, it's sure it's still needed. It's still needed because yeah, it's still OpenFOAM. So yeah, I have no idea what to say more. Let's go for another one. Espen Kroch is asking, is it possible to lease a license for a limited time period, for example, for 3 months? I think so. Yeah, I think so. Please, Espen, just contact us and let's make a deal. I think it's pretty possible. Yeah. Not by default, but yes, it's possible. Another one, can we use ANSYS files in Turbomachinery CFD for making simulations? Question from Nahale. So I'm sorry for spelling your name from Nahale. Yeah. Actually, yes. Actually, this was the case. So you can import the mesh. You can import the mesh from to the OpenFOAM, and yeah, then you can use it. Of course, you cannot take ANSYS case directly, but after quick rewriting them into Machinery CFD or OpenFOAM, meaning and terms, yeah, then you can use it. Yeah, you can import any mesh, and you can import any settings, and you can automate it because it's scriptable, it's easy, and then you can run really many simulations automatically. Okay, can you define the properties for other gases? Yeah. I am interested in supercritical CO2 turbomachinery from Louis. Yeah, actually, this is a question. So by default, there is an idle gas, right? And this idle gas is by default, and it remains a question to me whether we can add other properties. It's a two special requests to me, so I would ask you to send us an email, and then we can make a meeting on it, and let's see what we can do. Mr. Frank Huber, would you please outline the geometry input and meshing process? Yeah. So what to say? So there's by default there's a configuration file with the extension .tcfd, which is a plain text file where all the settings is written down. It's a kind of configuration in a simple file, and usually the most of the cases has also the surface geometry with it, which is written in this configuration file .stl surface geometry files, and these and that's the default settings. And also you can import your geometry or your computational mesh from other external software, and that's the case of what we have seen today. But usually it's the configuration file and the surface geometry. Yeah. So yeah, for the details, that's what Radek did a while ago. So please contact us, Frank, for the details. Another question: can this software use GPU processors to speed simulations? Louis, not yet. We have a collaboration with Vratis, a Polish company. It was stopped for some time, but we look for it in the future, and I believe we will get back to it. So it's in the process, but things are not so fast. So we are in the process. No, not yet. Hankar is writing, does this CFD tool support optimization? Yeah, the same answer. It's in the process. It's in the process. We have German collaborator, CF Turbo, great guys from Dresden and Munich. We have close collaboration on designing, interfacing, and simulating tools, and we are also working in optimization tool. And I believe it will be introduced, or at least the first version will be introduced next year. So not yet, but it's on the way. Sandeep Nair is asking, can we model vortex introduced vibration analysis, turbomachinery pump, and open foam? I'm not sure. I think I would say not directly, at least not directly. But Radek, what do you think about this question? Not sure.
Well, in this version not. In this version not, because now there is no connection to the rigid, how to say, to the rigid body analysis. So there is no movement of the solids included right now. But it is a question of the next version, and we are already think about it. But this version doesn't provide it.
Okay. So Sandeep, I would ask you to send us an email, and perhaps we can take a look on it. Maybe it's not exactly the solid. Anyway, yeah, this was this question. By the way, we are working, and we have already finished the big project on aeroacoustics on fans, and in the next version of Turbomachinery CFD, very likely there will be an aeroacoustic model for fans included, and there will be there will be a function which follows the sound spectrum and the sound characteristics. So it will be a new feature in the new version of the Machinery CFD. We are developing it in a big way. We are developing it quite strongly, and then the new features are coming, and we believe that this would be the best software in the market quite soon. Okay, so can you please send this webinar after it ends to my email, Gobia? Yes, the webinar will be, the webinar will be uploaded. The video will be uploaded to our YouTube channel and also to our webinar channel. So anybody would be able to watch it again really carefully, especially the technical part which Radek did, and everybody would be able to think about it again. I'll go to the question, back to the questions, because there are pretty a lot of them. So Yeah. Okay, Andrew is asking, which boundary conditions are used at the interfaces between the components? So, Radek, would you answer this question? I read it again. Which boundary
Okay.
conditions are used at the interfaces between components?
Well, I guess I already said it.
I will switch the presentation to you, back to you, and
Okay.
now you can
Okay, I
show.
click online. Well, if I go to this axial pump case and to this components definition and component connection, so there is two options how to connect two components. First option is to use AMI approach. The second option is to use mixing plane approach. So for this particular case, when you have a different number of blades, you have to use for the stator rotor interface, you have to use mixing plane approach, and the number of mixing planes you easily define here. For example, here at the impeller outlet, which is the interface between impeller and the stator, here is set 10 mixing planes. So for this interface, you have to use mixing planes, and for interface where the interface are the same, you can use AMI simply by clicking on it and setting 0. So two boundary conditions, AMI or mixing planes.
Okay, thank you, Radek. It was comprehensive. Yeah. So I'll go because we have some more questions, so I'll go through them. Uh, can you please, and we did this. What is your YouTube channel then? Again from Gabia. Yeah, so maybe I should. Yeah, maybe I can. Yeah, our YouTube channel is basically this, and you can go there pretty easily. You can go to anywhere to our website, and each of our websites has like social media panel, and the red one is YouTube channel, right? So click on our website, in CFD support website, you can click on it, and then you will find yeah, I think it's straightforward. Our YouTube channel where you can click some videos. Also, by the way, on our website you can find some tutorials either for Turbomachinery CFD and for standard OpenFOAM. You can, which were like really good learning source. So we believe it might be helpful for you. And yeah, which brings me back to the webinar. Okay, I'll take a look for the back to the questions. Yeah. Thank you for your answers. You're welcome. Can you please let us know the cost of AMC? Yeah, actually, I'm not sure what is AMC. Okay, so I was not sure what is AMC. So I don't know. So this is what I can't answer really, and I think this is almost it. I can't see any more questions. So
maybe if I can.
Yes, please.
I don't know if we answer it. Could you please outline the geometry input and meshing process? Frank asked. We didn't answer it,
so
I guess.
I thought we were there, but you can please Radek, answer it. Answer this question, please.
Okay. So basically, because this case was about using the external mesh, and if you are using just the STL or just geometry definition, so I will use here is, for example, I have your radial fan case, which uses the STL geometry. Okay, so I will just clear it. So at the beginning, you have just configuration file and STLs, and this STLs defines your geometry. So I just open it. I will open the STLs just to see. Okay, apply. Okay, somebody's broken here. Okay, again. I will close my paraviews, and again I will open it again. Apply. Okay, well, so again, I was too fast. Yeah, perfect. So here's the example of using just the STL geometry, and the TCFD creates the mesh automatically. So the input are STLs, which defines each regions. Here we have just the impeller part and the volute part, and the STLs only, let's say, only important thing about STL is that it must define waterproof regions. After that, inside the geometry definition, you just pick up each STLs. For STLs, you define the type. For example, for impeller blade, there is a type. Okay, impeller blade leading edge, and so on. You check just what is rotating, and here you will define the levels of refinement. So maybe there is no time to explain how snappy hex mesh works, but in general it works that it creates a background mesh, which is defined here, the size of the background mesh, and so on. Afterwards, you define the level of refinement for each boundary. You will just define mixing planes, for example, between impeller parts and the stator parts, and that is all. So it's really similar to using external mesh, but now your mesh defines the STLs, and afterwards here in TCFD manager, you will just write the case, run all, and in this create mesh, it runs the snappy hex mesh, which creates the computational mesh. So, but for more details, because maybe here is no time to explain it in more detail, if you are interested, then please send us an email, and we will gladly answer your questions. So.
Yeah, exactly. Yeah, thank you, Eric, for this. And there's the one last question. The Shankar explained what's AMC, which is annual maintenance contract. So, yeah, which brings, yeah, the presenting back to me. So I only say, yeah, it's basically it's here. Yeah, those are the costs. So universities pay 3,000 euro per year, and private companies pay 12,000 euros per year, and that's the pricing. So there is the maintenance, updates, and also technical support, which is, I would say, it's extraordinary, and we are proud of it. We solve every issue, we help, we really support. It's real work in it, and that's the maintenance. So in some sense, we can say it's not paid. It's not software what is paid for. It's paid for the delivery, and then for the technical support and the updates. When we deliver the software, it's always perpetual. You can keep it for the ages. It's unlimited in number of users, jobs, or cores, and you can keep it forever. So it's really unlimited. And what is paid for is the delivery, which is important, and technical support and the updates. And after the technical support ends, you can decide not to go on with us, but you can keep everything. You can use Turbomachinery CFD for forever. So it's big benefit, and it also makes us to really do our best to convince you it makes sense to continue with us the next year and the next year and and for all the years to come. I think it's time to conclude, to finish. So maybe we can switch the cameras back on. Now people can see me. Hi, back again. Yeah, thank you for being here. Thank you for coming. It was a pleasure for us being here with you today. Thank you for your attention. Stay tuned to us. The webinar will be uploaded to our YouTube channel, so you can follow us and you can watch it again anytime. It was a pleasure. So thank you for your time, and yeah, it's time to go. Bye bye.
Thank you.
Yeah,
Bye.
bye bye bye. Thank you for being here. Okay, thanks. The end webinar.